Welcome back everyone. In this lecture we will continue to study the basic properties of natural numbers. So, let me begin with defining an order on the natural number, which is the usual order that actually inherited from the real numbers. But anyway, we haven't defined real numbers yet. So, better we just define the order on the natural numbers using natural numbers. So, here is the order. So, we use this n to denote the set of natural numbers. So, we are going to use the standard notation 0, 1, 2, 3 etc. So, now given two elements, let us say n and m belongs to n, and we want to say that n is greater than or equal to m if so the size of n should be bigger than the size of m. So, that you can actually use this algebraic property to define. So, if there exists a in n such that n equal to m plus a. So, this we can take it as definition of order on n. So, now once we have defined this order, then we can actually see some of the basic properties of this order with respect to the addition and so on that we have in n. So, there are two important operations that are defined on n. One is the addition, another one is the multiplication. So, you can see that so I am not actually going to go through the definition of addition and multiplication on n. I am going to assume that you are all familiar with that. So, now we are going to actually see that this order actually will behave with respect to this addition and multiplication. Okay, so let us write down all the basic properties. And now it is convention that whenever n is not equal to m, we write n greater than m. So, whenever n is not equal to m and n is greater than or equal to m, this is all standard. Similarly, you can also talk about m less than n. Okay. So, now what are all the properties of this order that we have defined? It is easy to see that the ordering on n, it is reflexive, anti-symmetric and transitive. So, let me just write it as a proportion. So, we take this the order on defined on n and it satisfies the following properties. So, the ordering is reflexive, anti-symmetric and transitive. So, what is the meaning of that? That means a is always greater than or equal to a. So, that is the meaning of reflexive. So, then the second meaning, so anti-symmetric means if a is greater than or equal to b and b is greater than or equal to a, then that should imply that b equal to a. The third thing is the transitive, which says a greater than or equal to b and b greater than or equal to c, that implies that a is greater than or equal to c. So, since the proof of this basic fact is easy, so I will leave it to you to check. So, I am going to just check one or two properties that are satisfied by this order and basic operations on n, and the remaining thing I am going to leave it to you to check. The second property, that the addition indeed preserves the order. So, that means for all a greater than or equal to b. Okay. So, let us start with a b being. So, let us say a, b, c, they are given to be elements of n. Then if a greater than or equal to b and c is in n, so then we can say that a plus c is greater than or equal to b plus c. Okay. So, the way we prove is that we already know that Okay, let me just outline the proof here. So, A greater than or equal to B implies that there exists alpha in n such that A equal to B plus alpha. Now, if we add C on both sides, add C on both sides, so then we get A plus C equal to B plus C plus alpha. So, that implies that A plus C is greater than or equal to B plus C. Okay. So, like I said, the proofs are not very difficult. So, one can actually just write it down. So, now what is the third statement? Again the multiplication is also preserving the natural ordering on n. So, that means if A greater than or equal to B and C is given to be natural number, so then AC should be greater than or equal to BC. The way we prove this again, you have A equal to B plus alpha, then multiply by C on the both side, you get AC equal to BC plus alpha C, that implies that AC is greater than or equal to BC. Okay. So, now we can actually characterize when A will be bigger than actually C. So, the following are equivalent. So, this is maybe we can take it as the fourth property. The fourth property is that these statements are equivalent. The first statement being A is greater than B. The second statement is same as A is greater than or equal to B plus 1, and the third statement is that A greater than or equal to B plus D for some D in n such that D is greater than or equal to 1. Okay. So, these three statements they are equivalent. So, it's again easy to prove. So, I will leave it to you to check. The most important property is that law of trichotomy, which we have it for real numbers, which that is also true for natural numbers, which can be proved again using piano axioms or the way we constructed the natural numbers. So, this is the law of trichotomy. So, which says that given this A and B in n, so exactly one of the following is true. So, exactly one of the following is true. So, first you can have A equal to B, and the second thing, in case A is not equal to B, then we can have either A is greater than B or A is less than B. So, this or this or this. Okay. So, these three possibilities are there. So, this is again tells you that given any A B, they are comparable, either A is greater than or equal to B or A is less than or equal to B. So, that also we have. So, now I am going to actually demonstrate so how to use these mathematical inductions in appropriate places. So, like I said, we have these three statements, they are equivalent. One is mathematical induction and mathematical strong induction and well ordering principle. So, like I said, each statement has its own merit. Sometimes in very particular situation we can use cleverly one of them. Okay, that will actually help us. So, that is what I am actually going to do now. So, the most practical way to use the mathematical induction is that you must have learned it in the smaller classes. So, you take a statement that involves n. So, let us call that statement P of n. So, this is the statement. So, it is a mathematical statement. It could be, for example, identity that involves n, or it is a mathematical statement that has, for example, like statement like any integer is product of prime numbers. So, such statement we write it as P of n. So, this is mathematical statement depends on n. So, now what we want to do, like we want to verify this mathematical statement. So, then in practice what we do, first we verify that the procedure is that first step will be check whether the initial condition holds or not. So, check first P of 0 is true, okay. This is the step 1, and the step 2 will be assume that P of n is true, and using this prove that P of n plus 1 is true. Okay. So, this is how actually one goes about proving the statement involving n is true for all n. So, then from this step 1 and step 2 we conclude that P of n is true for all n in n. Okay. So, this is how actually we use mathematical induction in practice. Indeed, if we think about it, what we are doing. So, if the statement P of n is given, we are constructing this A, which is a subset of n, such that that P of n is indeed true. So, which is a subset of n. So, then the step 1 indeed verifies that 0 is in A, and the step 2 indeed verifies that if you assume that n is in A, then that implies n plus 1 is in A. Okay. Now, using these two, we are just concluding A is entire n. So, that is what indeed happening in the process. So, when we are actually dealing with a strong mathematical induction, so then what we do, we have this statement P of n. As a first step, we verify again P of 0 is true or not, and the step as a step 2 what we do, we assume that P of k is true now for all k, which is smaller than n. So, then we verify assuming this, we verify that P of n is true. Okay. So, this is how we actually use mathematical strong induction. Then we conclude. So, then we conclude that P of n is true for all n in n. Okay. So, this is what we do in mathematical strong induction. So, we just call it as strong induction. Okay, let us see some example to demonstrate this. If we are actually looking at the mathematical induction, for example, statement like this, which you must have proved using mathematical induction, that 1 plus 2 plus 3 plus etcetera plus n is exactly given by n into n plus 1 by 2. Okay. So, this is something like involving n, which is an identity about numbers involving n. Okay. So, now you want to prove this. So, the one way to go about it, you just prove it for actually initial cases, and then you just verify it for assume it for n, and then you just verify it for n plus 1. Okay. Then that will actually tell you that this statement is true, because our natural number starts with n, we can just add 0 in it, there is no harm in that. So, now let us verify this. So, this is the statement P of n, and if we take P of 0, it is clear that 0 equal to 0. So, the verification is done, the step 1 is done. So, assume the result is true for P of n. So, P of n is true. So, that means when you are taking 0 plus etcetera up to n, it is n into n plus 1 choose 2. So, now we want to verify claim is P of n plus 1 is true. So, how do we do this? Just take 0 1 plus etcetera n plus n plus 1. So, now we know that if we take the first n terms, actually n plus 1 terms, that is going to give us exactly n into n plus 1 divided by 2. So, then we are adding this n plus 1 here. So, now you can easily verify by doing this simple computation that this is going to be exactly 1 by 2 times n into n plus 1 plus twice n plus 1. So, now what we can do? We can take n plus 1 common. So, then it becomes n plus 1 times n plus 2 divided by 2. So, now it is clear that 0 plus 1 plus etcetera plus n plus 1 is given by exactly n plus 1 times n plus 2 divided by 2. So, that verifies that P of n plus 1 is true. So, now from mathematical induction we conclude that this is true for all n in n. Okay. So, this is how we indeed prove this result. So, sometimes what happens, our mathematical induction might start with some k, and if it is actually happening consecutive from k onwards, then still we are okay with that. So, for example, what I am trying to say, you have a subset of k plus 1 etcetera. So, I am doing the shifting, okay, such that k is in A, and whenever n plus k is in A implies n plus k plus 1 is in A, okay, for all n greater than or equal to 0. So, these two things satisfies. So, then one can easily conclude that A is exactly equal to k plus 1 etcetera. Okay. Maybe you can take it as exercise and you can use the original mathematical induction to prove this. Okay. So, that means one can actually start the induction at some k, there is no issue. Again, this shifting that I have done it in the forward direction. So, one can also do it in the backward direction. For example, the induction can start with -1 or -2 onwards, there is no issue. Okay. So, it depends upon what identity that we are doing. For example, if I drop this 0, then you can see that here the induction starts with 1, not with the 0, and that is not a big deal because it is not going to cost us anything. Okay. So, now let us see like some situation where mathematical strong induction can be applied. So, the statement that I was mentioning, that any positive integer that can be written as product of prime numbers. So, that can be proved using actually mathematical strong induction. So, you start with n. So, here is the statement. So, let me call it P of n. So, any n can be written as product of prime numbers. I am not worried about the uniqueness and so on. I am just only focusing on whether it can be written as product of prime numbers. So, now how do we verify this? To begin with, there is nothing to verify for P of 1, because when n equal to 1, nothing to prove, because it is like an empty product. So, we can allow like 1 is unit, it is not a prime. So, you can just take 1 equal to 1, which is like you can treat the right side as empty product. And if you are not sure, then maybe you can go to the second thing, and then you can see that 2 is written as 2. So, 2 is a prime. So, here also the statement is verified. So, now you assume now the statement for up to is true for all k smaller than n. Okay. Assume that. So, here I am using actually mathematical strong induction, because if you think about it, mathematical induction may not help that much, because now we are talking about prime factorization, it is about the multiplication. So, by knowing prime factors of n plus 1, there is no way to get the prime factors of n. So, that is actually impossible task. So, n plus 1, let us say it is written as some product of primes, then from this it is very difficult to actually write down what will be the other way. So, if you assume that n is product of primes, then it is actually very difficult to write down what will be the prime factors of n plus 1. So, that is why mathematical induction is not that helpful, but here you can see that if you assume mathematical strong induction. So, then to begin with we want to prove it for n. So, if n is a prime, then again nothing to prove. That is because you can write it as n equal to n. So, now this case is done. So, this is like a case 1. Now, the case 2 will be what if n is composite. So, then n will be written as some a times b, where a is less than n and b is less than n. So, now what we can do? We can use mathematical induction on a and then mathematical induction on b. Okay. So, then that would imply a will be written as some p 1 etcetera p r product of primes, and similarly b will be written as some product of primes q 1 etcetera q s. So, then if you put them together, a b will become p 1 etcetera p r times q 1 etcetera q s. So, that means n is exactly given by p 1 etcetera p r times q 1 etcetera q s. So, this proves n is also product of primes. So, here mathematical strong induction helps us more. Okay. So, we will actually use well ordering principle very often. So, anyway, I am going to talk about cardinality in a minute, and there we are going to use well ordering principle a lot. So, I will not demonstrate right now the use of well ordering principle. I will wait for that cardinality business. Okay. So, now you can actually generalize this kind of result even for any non-zero polynomial defined over real numbers, complex numbers and so on, and that will be done in this course later. Okay. So, now we will actually start with some counting arguments. For that, first what we want to do is we want to actually define what is cardinality. So, the notion of cardinality is defined by Cantor. So, who actually talked about various different infinities. So, people actually those days understood what is finite and so on, but people were not that much worried about various different types of infinities. So, either finite or infinite, that's all they cared about, and between infinities they did not care about various types of infinities that could be even possible. Okay. But we will see that in a minute. One can also talk about various types of infinities. Anyway, so let us begin with defining what is a cardinality of a set. Okay. So, before defining different cardinalities, let us first understand how to compare two given sets. So, what we want to do is we want to understand the cardinality of a set. So, that is what we want to do, but to understand the cardinality set we need to first understand how to compare two sets, because the whenever we talk about cardinality, even if you take finite sets, so we are making comparison between two sets only. Okay. So, that is why we need to first understand how to compare two sets. So, let us say x and y are given sets, and since we are going to talk about cardinality, the number of elements in that set and so on. So, we better assume both of them are non-empty sets. So, and we do not need to assume that anyway, like if one of them empty, if they are comparable, then another one will also be empty. Okay, so how we are going to compare this x and y? If we think about it, we have this x here and then we have this y here, and we want to kind of compare the elements that are in x with the elements that are in y. So, that means I would like to say the number of elements in x is same as number of elements in y. So, one way to put that in more mathematical rigorous definition is that, so given one element here, let us say x, if you are able to find another element in y, which you just abstractly think as mapping x to y. So, then like for each element in x, if you are able to find elements in y and vice versa, then you are done. So, then you are making some kind of one to one correspondence between them, and that is going to tell us that okay, the number of elements in x will be same as number of elements in y. So, that is what we are indeed going to do. So, we are going to say that x and y, they have same cardinality if there exists a bijection from x to y. So, we say x and y have same cardinality if there exists a bijection, call it f, from x to y. So, recall that bijection mean it must be both injective as well as surjective. So, injective means given element in x, there is a unique image inside your y, and the pre-image is also unique. Okay. So, given y, you have unique pre-image x inside x. So, like two elements in x should map to two elements in y, and surjective means each y will be coming from actually some x in x. So, that is what it means. So, f is both injective and surjective. Okay. So, then you say that they have same cardinality. Sometimes we call it, when sometimes we coin the term, it is equinumerous, and we write in this case the mod x equal to mod y, or the cardinality of x equal to cardinality of y. So, this symbol just says that we are talking something about the cardinality, but of course, we are dealing with abstract sets. So, it could be infinity, but again like we do not know the different notions of infinity and all yet, we do not know about that. So, that is why it is okay to say given two sets whether they have same cardinality or not. So, whenever we write mod x equal to mod y, that means there exists a bijection from x to y, that is all we can say. So, now with this we will be able to actually define various notions. For example, let us start with finite, and we say that a set is finite, x is a finite set if either x is empty, in that case we can also call it finite, or there exists n greater than or equal to n such that you have a bijection, and a bijection f from I n. So, I n is just 1 to n, okay, such that x and I n, they are bijectively corresponding. So, let us put it like this. and f such that is bijective. Okay. In that case we say x is finite. And what is infinite? Infinite is just a negation of finite. X is called infinite, which is just not finite. Okay. So, now we have this natural numbers, and natural numbers like we said, it is the smallest infinite set. Okay. So, then some sets that are actually having same cardinality as natural numbers deserves a name, and you call some set is countably infinite if it has same cardinality as n. Okay. So, if cardinality of n is same as cardinality of x, then we say x is countably infinite. And of course, finite sets are also countable only, because when the terminology countable means we should be able to count them. So, then broadly speaking we say x is countable if either it is finite or it is countably infinite. Either x is finite or countably infinite. And if x is not countable, you call it uncountable. X is uncountable if x is not countable. Okay. So, various notions are actually coined here. You have finite, and opposite of like negation of finite is not finite, and you have countable, and negation of this is uncountable, and within countable you have finite and countably infinite. So, you have all these things, you have finite, you have countably infinite, and these two form countable, and you have outside uncountable. Okay. So, these are all the notions that we have introduced, and we will see that later within uncountable itself we can talk about various types of infinities. Okay. So, maybe I will actually do that in the next class. So, I will actually start with finite sets, and we will first understand how to actually define the cardinality of finite sets and why it is well defined, and then later we will move to countably infinite sets, and then finally like we will have a brief discussion about various types of infinities. I will stop here, we will continue in the next class. Thank you.